Hello everyone, in this video we'll discuss the concept of assembly language in general and specifically we'll focus on MSP430 assembly programming. First we'll see what instruction or instruction code means. Then we'll quickly go through the instruction set architectures, RISC and CISC, and instruction types and formats. As the fourth topic, we'll see the 7 addressing modes in assembly programming for MSP430. After the addressing modes, we'll see the conversion from the assembly code to the machine code. Our last slide will be about the stack, its LIFO, last in first out property, and push and pop instructions. Finally, we'll make examples on assembly programming in Code Composer Studio to see how the instructions are executed, and we'll observe the memory and registers to see the outcome of these instructions. In this slide, I've taken the explanation for instructions from the Professional Assembly Language book. At the lowest level of operation, all computer processors like microcomputers, mini-computers, and mainframe computers manipulate data based on binary codes defined internally in the processor chip by the manufacturer. These codes define what functions the processor should perform, utilizing the data provided by the programmer. These preset codes are referred to as instruction codes. Different types of processors contain different types of instruction codes. Processor chips are often categorized by the quantity and type of instruction codes they support. This is a very brief explanation for instructions. We can add smartphones or microcontrollers processors to this definition as well. Okay, now that we know what an instruction is, let's see how a microprocessor knows which instruction to run. Program counter is used to inform the processor to specify which code to run next. Program counter is one of the 16-bit core registers in the CPU. Program counter can also be called as instruction pointer in other environments. The instruction set of the MSP430 consists of 27 instructions. However, in addition to these, there are 24 emulated instructions which are actually derived from the original instructions. Now let's see RISC and CISC in more detail. We can speak of two different types of computing architecture, RISC and CISC. RISC stands for Reduced Instruction Set Computing, and CISC stands for Complex Instruction Set Computing. Main differences between RISC and CISC are listed in this table. While the CISC is the initial microprocessor architecture, RISC has been developed in the 1980s. In CISC, instructions take several clock cycles, however in RISC there are single cycle instructions. CISC has an emphasis on hardware, while RISC has an emphasis on software. In CISC, we can speak of efficient use of RAM, however in RISC, there is a heavy use of RAM. In CISC, there are complex and variable length of instructions, while in RISC, there are simple and standard instructions. Here we can see that there are three types of instructions for MSP430. Double operand, single operand, and jump instructions. There are 12 double operand instructions, and these two operands are source and destination. The operation is done with these two operands and the result is written to destination. In single operand instructions, we have only one operand, which is the destination, and there are 7 single operand instructions. And we have 8 jump instructions. In addition to this, there are 24 emulated instructions. These instructions are just for making the code more readable. They are replaced by the original instructions during the compiling process. Here is the whole list of the double operand instructions. In the list, we can see arithmetic instructions such as add, subtract, or logical instructions such as AND or XOR. In this slide, we can see single operand instructions. Push is one of the instructions that we'll use while accessing the stack. Here's the list of jump instructions. Jump instructions override the program counter. Conditional jumps support program branching relative to the program counter and do not affect the status bits. For the emulated instructions, you can check the MSP430 family user guide. In this slide, we can see the details of the double operand, single operand, and jump instructions. We will see this slide in detail while we are examining the conversion from the assembly language to the machine language. The details of these sections are listed here. AS stands for the addressing bits responsible for the addressing mode for source. So we have AS here. S register stands for the working register used for the source. We have S register here, or S or destination register here. AD stands for the addressing bits responsible for the addressing mode for destination. We have AD here, and we have AD here. D register, the working register used for the destination. We have the D register here and here as well. B or W stands for byte or word, 0 stands for word, 1 for byte, and we have the byte or word selection in these sections. And source and destination are the two operands for the instructions. Here is an example from the Code Composer Studio which includes some assembly instructions. Some remarks here. We need to pay attention that we are using semicolon for adding comments in assembly programs in CCS. And we need to use a tab before entering our instructions, otherwise the compiler can give an error. However, functions such as main loop and other user-defined functions should be entered immediately. In this slide, we can see the 7 addressing modes for the instructions in MSP430. We will see these in detail in our examples. And this screenshot is taken from the user guide, which gives information about the addressing modes. Now, let's see some instruction examples that are using these addressing modes. In the immediate mode, hash sign is used as a prefix to the number to represent a constant value. Ampersand sign is used for memory address. The 4 lines of move instructions inserts hexadecimal values to the addresses defined in the destination operands. The last move line inserts 0A0A hexadecimal value to the register 5. In the register mode, the operations are done on CPU registers. Here, the value of the register 5 is inserted into register 6. The absolute mode is used to reach a memory address and its content directly by the ampersand sign. In the first move instruction, the content of the 0200 memory address is inserted into register 9, while the second move instruction inserts the content of the address 0200 to the 0206 memory address. In the symbolic mode, memory locations are represented with words. The first move instruction inserts the content of the program counter to register 5. The second move instruction inserts the P1 in register's content to register 6. Pay attention that since the P1 in register is an 8-bit register, that's why move.b instruction is used. P1 in register holds the values of the digital input port 1. In index mode, RY holds the reference address and X is the increment to that reference address. Pointer operations are performed in the indirect register mode. Add symbol is used for pointer. In the first move instruction, CCCC value is stored into 0202 memory address. In the second move instruction, 0202 value is stored into register 10. In the last move line, the content of the address stored in the R10 register is inserted into register 11. Here it is CCCC. Indirect auto-increment mode uses the indirect register mode. Indirect auto-increment mode also allows table processing. Register values incremented after each operation automatically. Now let's see how the conversion is done between programming languages. In this slide, we can see the relationship between high-level programming language such as C and assembly language. Our code, which is written in a high-level language such as C, is converted to assembly language before being loaded as machine code to the microprocessor. This is done by the compiler we are using. In our case, for MSP430, it will be CCS, Code Composer Studio, and we will be able to observe this conversion in the disassembly window in CCS. Actually, the assembly code and the machine code are not the same thing. The assembly code that we write or the code that was converted from the high-level language, such as C, is then converted to the machine code or machine language based on the instruction set of the processor that we are using. So, in this example, the first move instruction, which inserts the 0009 hexadecimal number to core register R5, is shown in machine code as 4035 0009 hexadecimal. The second line, which inserts the 0006 hexadecimal number to core register R6, is shown in machine code as 4036 0006. And in the third line, which adds the content of the register 5 to the content of register 6, is shown in machine code as 5506. Okay, but you should be asking yourself this question. How is this conversion done? To understand it, we should see the details of instruction formats. In order to understand how the assembly language was translated into machine code, we should understand the instruction formats that are used by the CPU that we are using. Here we can see the instruction formats for the CPU of the MSP430. In the MSP part of the 16 bits, we have the opcode which is pointing to the assembly instruction. At this point, let's quickly take a look at the instruction map of the MSP430. This instruction map is taken from the user guide, and we can see that each instruction has a different code. Let's take move as an example. We can see that the most significant 4 bits and nibble as short has the value of 4. And the add instruction's most significant 4 bits has the value of 5. Now let's focus on double operand instructions and see how the instructions in the previous slide were converted into machine code. The first instruction that we are going to examine is this one. Move 0009 hexadecimal to register 5. And be careful that we are using immediate mode as the addressing mode here. Now from the instruction map, we know that our opcode is 4 for the instruction move. So our opcode will be 4. We will have 0 here, 1, 0, and 0 here. Since we are using the immediate mode, we are not using any source register. This means that we will have zeros here. Now let's take a look at the AD and AS bits for the immediate addressing mode. For the immediate addressing mode, we can see that we will have AS as 1, 1 and none for AD. We will have 0 for AD and we will have 1 and 1 for AS. And from the instruction, we know that we are doing this on word level. So we are going to again have 0 here in order to indicate the word. And we know that our destination register is R5. So we will have 0, 1, 0, 1. If we convert this 16-bit binary value to hexadecimal, we are going to get 4 from this, 0 from S register, and we are going to have 3 from these bits, and from the D register, we are going to get 5. And in the next 2 bytes, we are going to give the value that we are going to store. So that will be 0, 0, 0, 9. Now you can understand how we converted this assembly instruction into machine code. If we go to the previous slide, we can see the machine code translation, and that is 40350009. The second example will be similar. So let's examine this command and see how it's converted into machine code. So the instruction that we would like to convert into machine code is add word R5 to R6. So we know that the instruction that we are going to convert is the add instruction. And we know that the opcode for add instruction was 5 from the instruction map. So we are going to have 0 here, 1, 0, 1 for the instruction. And the source register that we are going to use is R5. So we can directly write it 0, 1, 0, 1 to indicate 5. Now let's go back to the addressing modes and see what AD and AS will be for the register mode. For the register mode, you can see that both the AS and AD will be 0. So we will have AD as 0 and AS as 0 as well. We are doing the operation on word level, so this bit is going to be 0. And our destination register is R6, so we are going to write 0, 1, 1, 0 for R6. Now let's combine this. We have 5 here. We have another 5 here. We have 0 from this section. And we have 6 for the D register. So you can see that this assembly instruction has been converted into machine code as 5506, just like in this example. Our last slide is about the stack. The stack is a LIFO, last in, first out address list. The stack pointer is set to 0400 hexadecimal in MSP430 device. This is the highest memory location for stack usage. There are two stack operations. Push adds or pushes as the last entry the value to the stack, and pop gets the last entry from the stack. You can relate the working principle of the stack to a coin holder. The last coin that you push into the coin holder will be popped first. Stack pointer can be observed from the registers window in CCS. Now let's make some assembly programming examples in CCS. Our first example will be about the push and pop instructions. We are going to be pushing 4 values to the stack, and then we are going to pop the values from the stack and insert them to register 6. As you can see, we have a tab before the instruction, and we are using semicolons for the commands. Let's click on debug. And let's go to the memory browser. And instead of clicking resume, let's click on assembly step into to see what happens in each line. Now lines 19 and 20 will be executed as I click on the assembly step into twice. And now we are in the push command. Let's observe the memory browser while we are clicking the assembly step into button. You can see that hexadecimal 6 value has been pushed into the stack. Let's click on assembly step into once again and see what happens. And now we have pushed hexadecimal 4 into the stack once again. So the first value that we had pushed is residing in the 3FE memory address. And the second value that we pushed is in the 03FC address. Let's click on the assembly step into twice and see the memory browser. Now we can see that we have 6 value in address 3FE, we have 4 value in 3FC, we have 2 value in 3FA, and we have 0 at 3F8. Now let's continue clicking on assembly step into and execute the pop commands. Before that, let's open the core registers and be ready to observe R6. As you can see, the value of R6 is now 0. You can observe the LIFO last in first out property here. So the last value that we had pushed to the stack was 0. And when we executed the pop instruction, we popped the value 0 since we need to observe the last in first out property. If I click on assembly step into once again, I'm going to observe 2 in the register 6. Let's see that. You can see that it's updated. Let's click on once again. You can see that it's 04 and the last command will get 06. So the first value that we had pushed to the stack. Now let's go to our second example for assembly. Our second example is rather a longer one, and we are going to execute several instructions here. So let's see the main loop. We have some move commands, we have an add command, decimal add command, subtract command, we have the logical AND, we have XOR here, we have right shift, we have swap bytes, and etc. So first let's debug the code. And let's open core registers for observing them. If we click on assembly step into twice, it's going to execute the lines 19 and 20. So let's execute them. And let's continue starting from line 26. When I click on assembly step into, we are going to expect that we are going to get the value 9 into register 5. Let's see that. You can see that value 9 hexadecimal has been inserted into R5. And in the next line, we are going to insert 0006 hexadecimal to R6. And in this line, we are going to add these values together. And remember that the result of the operation is going to be inserted in the destination. So in our example, it will be register 6. So we are expecting that the value 9 and 6 will be added, and it's going to be stored in R6. Let's click on assembly step into. You can see that the values are added and it's stored as F, meaning 15 in decimals, in R6. So let's insert 06 in R6 again to have our initial state. And now we are going to use the decimal add instruction. With the decimal add instruction, the hexadecimal values are going to be treated as decimals. So let's see what this means. When I click on assembly step into, you can see that the value 9 and 6 was added together and the result is shown in decimal form, even though we have hexadecimal demonstration here. So let's click on assembly step into once again and go back to our initial state where R5 has 9 value and R6 has a value of 6. Now we are going to subtract R5 from R6. So be careful. We are subtracting R5 from R6. So this is not R5 minus R6. So let's click on assembly step into. Okay. Now the result of the operation is stored in R6 and it's FFFD. We are expecting -3 as the result. But remember the 2's complement demonstration of the negative numbers. You can go back to our previous lesson and see it by yourself how to calculate the 2's complement demonstration. Now there is one more important thing here. We have made an operation and the result has been inserted into R6 and its value is FFFD. But how can we understand that this value is negative? So if we go to the status register, we can see that the negative bit has been set after our operation. So if you read the description, you can understand it by yourself. This bit is set when the result of a byte or word operation is negative and cleared when the result is not negative. So the operation that we had done, which is subtracting 9 from 6, which is equal to -3, the result is negative. So after this operation, the negative bit has been set to 1. And now we know that the value stored in R6 is a negative value and it's represented in 2's complement form. So this is how we can understand that it is -3, not FFFD. Let's continue observing the registers while we are clicking on assembly step into. Here in this line we are inserting value, but we are demonstrating in binary. So let's click on assembly step into, and you can see that we have inserted F in hexadecimal form to R5. You can see that this value is F as well. And in the next line, we are inserting the value 3 to R6. And now in the next line, we are going to AND these two values. So let's click on assembly step into once again. But before doing that, let's right click here and change the number format to binary in order to observe better. Now we are going to execute the AND instruction, which is going to AND R5 and R6, and it's going to write the result to R6. So the register 6 didn't change because when we use the AND operation between these two registers, the value is again 3 in hexadecimals, and you can see that it's already there in R6. So now in this line we are going to use the XOR instruction. We are going to do it again in R5 and R6, and the result will be written in R6. So let's click assembly step into. You can see that the R6 value has changed according to the XOR operation. In the XOR operation, if both inputs are different, the result is 1. Otherwise, the result will be 0. So in this line 39, we are going to right shift R6. And we can observe it in the best way in binary. So let's click on assembly step into once again and let's observe R6. You can see that the bits have been shifted to right by 1. So we had the 1 and 1 here. Now they are shifted to right by 1. And this command that we are going to execute will be swapping the bytes with most significant byte and the least significant byte. Okay. So it's better to go back to the hexadecimal format again. When we click on assembly step into, let's observe R5. You can see that 000F has been changed into 0F00. This was the last example for assembly language programming in MSP430. I hope it's been useful for you. If you have any questions, please write them in the comments section. Thank you for watching. Bye.